Everyone, this video is talking all about confidence intervals. So what's the general idea theory behind this? Well, the idea is you have some population. Let's just say your population is a normal curve for convenience. And you're taking 100 samples from it. So maybe you take a sample right here, and maybe you take a sample of data right here, and maybe you take a sample of data in the middle, and so forth. So you take 100 samples. That population has a parameter for its mean called mu. The idea behind the confidence interval then is if you take 100 intervals and you take 100 samples and you form 100 different confidence intervals off of those samples. If you're doing it at 95% confidence, that means that 95 out of those 100 intervals that you formed are going to contain this population parameter inside of it. And that kind of makes sense. If you look at the first equation in the chapter, confidence interval is equal to the population parameter, some population parameter, so sample mean, plus or minus z times theta over the square root of n. You can kind of see that you formed some interval with some confidence contained here, and the z is the confidence. The z is going to spread your interval out so that, because like z contains in it kind of like a little bit of probability, it's going to spread your interval out so that 95 of those intervals out of 100 are going to contain your population parameter. All right, so let's get into what these formulas are. This is the first formula you need to know in this chapter. So what's going on here? Well, the confidence interval, what I want to stress on this is that every time you see it in a question, it is always some interval. Let's just say 18 to 21, or some range. You'll see it in the form of an interval or a range. And what's essentially happening is the interval starts at 18, the interval finishes at 21, and your point estimate is always smack dab in the middle. So the right side of the point estimate is something called your margin of error. And to the left side of your point estimate is something called the margin of error as well. And you can sort of see this theory at work, because if you broke this down further, you could say x bar is plus or minus some distance from the mean. So remember, z is x bar minus the mu over the theta over the square root of n. And then it's times theta over the square root of n. These cancel out. And so you have an interval formed by some estimated distance from your population parameter. And that estimated difference is coming from the probability that you know Z contains. And this part right here, is all called margin of error. And it's always in every problem that you ever encounter going to be a single number. So 5 or 2, or in this case, this would be 1.5 is the margin of error in this example. So what I want to stress is that if you have a confidence interval, if you're predicting the population mean and you've predicted, GPAs range from 2.0 to 4 or something like that, or, count of people taking the final stats exam range from 18 to 21. If you have a confidence interval that's predicting something, you can always find the margin of error. And in this case, what you do is you do 21 minus 18 to get the full range of your interval, which is 3. And then half of 3 is 1.5. That's your margin of error. And then if you add 1.5 to the bottom, 18, you get 19.5. And in this example, that's your location of your point estimate. Because again, the point estimate's right smack dab in the middle of your interval. So if you find the full range, find half of that range, add it to the bottom, you can find where your point estimate is or where your mean is. All right, let's continue. Now, I want to emphasize that the next equations in your book all spawn from this first equation right here. So in reality, you only really need to know one equation for a confidence interval, and you can find the other ones. For example, the next important equation is using t. It's the confidence interval, and I'm going to label this equation 2. So it's a confidence interval equals your point estimate. I'm just going to assume it's x bar for now, plus or minus t times sample standard deviation over the square root of n. The decision rule here to go from 1 to 2 is, do you not at all have the population standard deviation? If all you have is your sample, then you're going to use 2. If you have some historical long run trend of like the scores are spread from like with a standard deviation of 0.2 or something like that, then you can use 1. But if you don't, if you just have your sample, you use 2. T has its own things going on, and that's going to be left separately. But essentially, if you see it, it's kind of the same thing. This is all functioning the same way. It gives you some interval based on a probability in T that's trying to predict your population parameter. Now, what is equation 3 and 4 that you need to know? Well, these come from the knowledge that your margin of error is this purple highlighted part. So equation 3 is margin of error is equal to z theta over the square root of n. And equation 4 is margin of error is equal to t, standard deviation of the sample over the square root of n. How we got this kind of makes sense. We're just taking this purple part right here, and we're taking this other purple part right here, and we're calling them out separately as margin of error. The final equation you need to know, because the rest of it just sort of varies on the parameter you chose, and I'll show you an example of that. The final equation you need to know is n is equal to parentheses, margin of error is on the bottom, and z is on the top, and theta over the square root of n. There's no square root of n on the bottom there. It's just on one side. And then squared. Where does this come from? Well, the idea is you want you sort of every experiment you do, you are doing a sample of a much larger population. So if your experiment is let's estimate the average GPA of an undergrad student, you can't obviously survey every undergrad student in the world for their GPA. But you can take a sample from maybe the business school or something like that. You can take a random IID sample, the meaning that my GPA doesn't influence your likelihood of your GPA. And let's say you want to know how big does the sample have to be so that 95 out of 100 times, if I pull the same independent random sample, my interval is going to contain the population parameter. There's a risk there because, 5% of the time, you might not be pointing to the population parameter. You might be pointing to, an error or something completely different in your interval. 5% of your intervals may be wrong, but you might want to set up the study so you reduce the risk of how wrong you are. And so you want to know your sample size for that. This is the equation you use to find that. And because you haven't done the study yet, you don't know anything about the sample. So equation 4 doesn't work to sort of do that. You have to use Z because you don't know anything about the sample. So like your theta might be sort of some history you have in this field where on average scores deviate by 0.2% in GPA or something like that. So if we're using Z, we're going to use this formula to find formula 5. And the way to do that is let's write the formula again. And the first thing we're going to do is we're going to multiply both sides by square root of n. And then we're going to divide both sides by margin of error. As you can see, certain things cancel out. Margin of error cancels out with margin of error. Square root of n cancels out with square root of n. And we're given this equation right here, which is square root of n is equal to z times theta over the margin of error. And then you can see it's a relatively simple step to go from here to this equation right here. You're just squaring both sides. So these are the 5 main equations you need to know. What I want you to get from this is that you really need to know one equation only. The rest of the decisions that occur sort of spawn from that one equation. So it's different manipulations of that one equation. What about if we have a proportion? Well, all you're going to do is replace certain values. So equation 6 becomes confidence interval is equal to P bar, which is just like if you remember the binomial distribution is like your probability of success plus or minus your z-score times your standard error. And in this case, standard error is P bar times 1 minus P over N. And this kind of has the same interpretations as before. So it's no different. It's just with proportions, you have to do standard error a little differently. This part is standard error. and your point estimate is different. That's all I want to show you today. This idea that a confidence interval is an actual interval with the point estimate smack dab in the middle and a single margin of error number that represents the distance from that point estimate to either side. All the equations spawn from one central equation. You choose t when you don't have theta, when you only have your sample. And there might be occasions where you want to estimate the population parameter, but you don't know what your sample size should be. And so you can use equation 5 for that. And just to get that point as my very last point to discuss, sometimes you'll see z and t written in this as z with the subscript of alpha over 2. That alpha is sort of telling you the following. When you're estimating by taking samples from the population, there's a certain percentage where you can sort of guarantee that your interval will contain the population parameter like 95% of the time. But there's 5% of the time you might form an interval, a 95% of the interval. You might form the interpretation that this 95% of the interval sort of contains the population parameter, and it doesn't. That alpha is that 5% of when you do a random sample, you form an interval to try to estimate the population parameter, and it doesn't contain the population parameter. So you'll have it with z a over 2, you'll have it with t a over 2. It's called the probability of a type 1 error, and it occurs everywhere in statistics. But in this case, you can think of it as like the probability of a false positive, or the probability of you basically taking a sample, forming an interval of 95%. And in your independent random sample, you say that, that we are 95% confident that this interval contains a population parameter. And you're wrong. The population parameter is over here or over here. That's what that alpha kind of stands for. It's the probability of a false positive of making that conclusion that you're 95% confident this interval contains a parameter when it doesn't. And so what you'll see here is confidence level. Confidence is housed in the Z or T score. That's going to be your middle part, the 95% or 99 or 98, whatever confidence interval you form. And that alpha is that type 1 error. It's going to be to the sides, your risk of making a wrong conclusion that your interval has a population parameter and it really doesn't. And sort of what you do is the alpha is both sides. So it's like this blue part of the interval and this blue part of the interval is both sides added together. So like A1, maybe it's the left side, plus A2, it's maybe the right side, is equal to your alpha or A, your total alpha. And so that's why you have the divided by 2, because you take your total risk of missing the parameter and you slash it in half to get both sides of your sort of interval tails. Anyway, I hope this was helpful. And if you have any questions, you're always welcome to let me know. Thanks. Bye.